Hi guys, welcome to our new chapter about exponential functions. A little quick vocabulary. An exponential function is going to take the basic form y equals a times b to the x, where a can't be equal to 0 because that would make the whole thing 0, right? And b cannot be equal to 1. Okay, because 1 raised to any power is just going to be 1. So it has to be this y equals a times b to the x, where x is actually our variable here. Okay, now you're going to notice that the dependent variable, the y, is multiplied by a constant factor. So when we look at a table of values like this, we are used to seeing in linear functions that this increases by a common added value. Okay, so if we add one on the top, we add one on the top, we add one on the top, we would like add two or add two, add two, add two across the bottom. In exponential functions, you are going to notice that we are multiplying. Our y is increasing exponentially. Here we're multiplying by 1/2, so it's getting smaller, increasingly smaller, but it is an exponential function because we are multiplying. That is the key thing to notice. Now, if you review what we would see when we were looking at a table of values for a linear function, we would notice that you would either add or subtract a constant factor or a common value on the top and the bottom. In order for it to be an exponential function, we have to multiply by a common factor. So this is not an exponential function, it's a linear function here. Now, when we are evaluating exponential functions, you are going to notice here's our base function. It is in the form of y equals a times b to the x, where here x is 3. So our base is 5, our power is 3, and what that means is 5 times 5 times 5. You guys are probably used to that. So when we simplify it or evaluate it, we get -2 times 125. Remember that an exponent of 3 is not the same as multiplying by 3. Be careful with exponents. It means 5 times itself 3 times, okay? That's the key thing to remember here. Now, when you are asked to evaluate an exponential function and they give you a negative value or to a negative power, I want you to look at your printout and notice that whenever anything is to a negative power, it's the same as taking whatever your base is, here it's that zero point 0.5, and putting it in the denominator. So we would have like 1 over 1/2. Now 1 divided by 1/2 is actually 2, right? And then 2 to the second power would be 4. So that's how we're going to evaluate our negative exponents. And I'm going to show you more examples of that here in just a little bit. So here you have a function. It's in the form of y equals a times b to the x, where x is either -2, 0, or 3. Now we just saw a quick example of how to evaluate something with a negative exponent. Here is going to be another example of that. So 2 to the -2 power. The thing you have to remember is that it would be this base, this 2 is your denominator. Okay, so it would be 1 over 2 or 1/2 squared. 1/2 squared is going to be 0.25, right? And then you multiply. So you may be remembering PEMDAS, that parentheses, exponents, multiplication, division, addition, and subtraction. You are going to have to take care of your exponents first before you do multiplication or division, okay? Now, I also want to talk to you about how to evaluate something to the 0 power. Here, anything to the 0 power is just 1. So we have 2 to the 0 power, which is just 1. So 1.5 times 1 is 1.5. Now, over here, our x is 3, so we have 2 to the third power, so it's 2 times 2 times 2, which is 8. There we go. We've evaluated them for these 3 different values for x. And you're noticing that our exponent, right, is the x. Now, when we are graphing, you are going to notice an exponential function is either going to grow exponentially, like we see here in this blue line, and that would be when your a is greater than 0, okay? And your b is also greater than 1. So this would be a positive situation where you are just multiplying and it's getting bigger and bigger and bigger. If you've seen graphs of coronavirus, it looks a lot like this. Now, when your a is less than 0, meaning your a or your coefficient out here in front is negative, you are going to notice that it is a reflection across the x-axis. And it never is going to be positive. It is always going to be negative, right? Because imagine you have a negative times whatever your b to the x power is. So it's always going to be a negative value. So this red line here is when your a is a negative number. Now over here, this is when your b, whatever you're multiplying by, is a fractional value. So it's between 0 and 1. It's a fraction or decimal that is greater than 0 but less than 1, okay? And when your a is positive, you are going to notice that it is going to shrink. And I want you to think about that. If you had 1/2 times 1/2, it's a quarter. Times another 1/2, it would be 1/8. If your b is some fraction between 0 and 1, it is going to continue to shrink. But it's going to be positive still. So it's just going to approach 0 and it's just going to get smaller and smaller and smaller. It's never going to quite be 0, but it's going to approach 0. Okay? Now, same thing when your a is negative, when you have a negative out here in front, all of these values are going to be in the negative zone. It's going to approach 0 as well, but it's still going to be negative. So remember, if you have a negative a, it's going to be all negative values. And your b, if your b is greater than 1, your graph is increasing. And if your b is between 0 and 1, your graph is decreasing here or approaching 0, okay? So you guys are going to get used to seeing these. I have a card sort for you guys to do, and you're going to have to evaluate those and get really good at just looking at the structure of the equation and matching it with its graph. So here is some more vocabulary. Your parent function is the most basic function. In a family of function. An exponential function, this would be when a equals 1, okay? Your asymptote is a line that the curve approaches but does not meet. So if we look at this, our asymptote here is 0. It approaches 0, but it doesn't actually meet 0. Same thing here. It approaches 0, but it does not actually meet 0. And your domain of the function would be all the input x values. So if we look here at our blue line, we know that this could extend forever along the x-axis that way and forever along the x-axis that way. So for this blue part, our domain is all real numbers. Now our range is the y values. And we notice that it would go from 0, so 0 is less than y is less than infinity because it could go on and increase and increase and increase to infinity. Okay? And so remembering that the domain is your x values, the range is your y values. For all of these, your domain is all real numbers. Your range is what's going to change. So here your range would be y is less than 0, and then it goes to negative infinity there for our y values. So you'll get used to seeing the domain and range here. And that's all the y values. Now here is a graph of this function. It's in the form of y or f of x equals ax to the ab to the x power, right? So you're going to make a plot table of values. So you can pick any x values here, plug it into your equation and evaluate to find f of x. Once you have that, that's your like x, y coordinate pair there, negative 2, 1, and you notice they plot that on the graph. Negative 2, 1, negative 1, 2, 0, 4, and that's how they've plotted this. Now I want you to notice that the parent function is g of x. So it's 2 to the x. If we were to just look at the graph of 2 to the x, it would be this black line. You notice that when we put a 4 out there, it moves the y-intercept of the graph. So I want you to see that the a, remember it's y equals a b to the x, the a tells you what your y-intercept is, okay? Here, I want you to look at the parent function. It's this black line. So our most basic function is this g of x equals 1/2 to the x power, okay? When we put a negative out in front, I want you to notice that that would be our a. So our a, or our y-intercept here for this one, would be a -1, okay? Which you notice here. In our parent function, the y-intercept is just 1, but that -1 means that our y-intercept is at -1, okay? So we will look at some more examples. I'll work some more of these out on paper, but for now, great job understanding exponential functions meet this basic form, y equals a b to the x, okay? And this is when b is greater than 1.